Hello folks, this is the second video tutorial that I'm doing for solving some very simple problems in the 3D experience which involve contact. I want to remind you that the solver in the 3D experience, FEA solver, is actually the Abacus program. And the first tutorial dealt with dealing with the shrink fit problem, as shown here on the right hand side below, where there is a brass bushing that is shrink fitted onto a shaft, I assumed in the first video, that this shaft is actually rigid. Okay. Uh, so the second tutorial that I'm going to do today is I'm going to assume that it's an analytical rigid surface. The difference between the two of them is that in the first tutorial, when you assume it's rigid, I have to mesh it with something. For example, I use shell element, and then I declare that those shell elements to be rigid, in spite of the fact that when you mesh it with shell element, you have to give it some dummy material, etc. So, for an analytical rigid surface, you don't have to mesh it, but there are. So you may be tempted to say, okay, analytical rigid surface then is better to do than the rigid elements, shell elements. Then why? What is the thing about the first tutorial? The problem is that analytical rigid surfaces, they must be either surfaces that are obtained by extruding a curved two-dimensional curve, or revolving a two-dimensional curve about an axis. So they are limited, although there are many situations where the surfaces are like that, such as punches, for example, etc. But if your surface does not meet those two requirements, you have no choice but to mesh it with either shell element or solid element, and then declare them to be rigid. Okay, so let me see for a second. I want to remind you that the key in this interference fit problems is that or shrink fit problem is in the interaction tab of the action pad here, action bar here, which we're going to use. Here is the contact interference icon, and for rigid surfaces, analytical rigid surfaces, we have to go to the abstraction. There is a tab here, which is abstraction, and one of them is analytical rigid surface. Tutorial 1 dealt with the one above it, which is rigid bodies. Now, this problem is basically mimicking some of the ideas from the reference that's shown below, although there, I think the fellow is using a different type of setup. Okay. So the dimensions are given here, and these are the same. These are the dimensions from that same tutorial, from that same reference, YouTube reference, and obviously we are assuming this is a deformable bushing, but the shaft, of course, is analytical surface, so we don't need material. We don't need material for it. Because of symmetry, we're going to take only 1/8 of the model, and standard properties of brass are used, and there's a frictional coefficient of 0.1 we are assuming between the surface of the shaft and the analytical shaft and the, uh, the bushing. Now, in the case of an analytical surface, just like the case of the, by the way, rigid surface, you can define a reference point, which can be, by the way, one of these corners or any point, and maybe even mass center of this surface. But anyway, I created a reference point out here because I want to be able to see it clearly, and the 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 restraints on this uh, surface is based on what you restrain the reference point to be. Okay. Now, shaft is modeled as analytical rigid surface, therefore there is no thickness to it, and there's no material. Okay. For the bushing, I model it with 4-knotted break elements, and nothing fancy here. We're going to use a general static analysis static step. And the only change that I made from default value is the initial time increment. I made it zero 0.1. I think the default is 1. I made it zero 0.1. This is the same thing that I did with the tutorial 1. We'll come to this later on, because once you get your result, then you can use 3D Experience to show you the symmetries that you have kind of lost because of the assumption that you made. And the other thing is that when you create your surface-based contact, you have to make sure that for the main surface, analytical ridge surface is selected. In the case of tutorial 1, we did face and face, face of this surface, this shaft, and the face of the bushing. But in the case of this problem, for the main surface, you have to go to the tree or somehow select the analytical ridge surface, not just the face. Okay, so let's go ahead and do that. Let me go up here. We go to 3D Experience. Let's create an assembly, because this is made of 2 parts. Assembly. And the first one is going to be our bushing. Okay, so insert, 3D part, and I'm going to call this thing bushing. Right click properties, uh, bushing. Okay, bushing. Okay, so to make it, I go to 3D shape. On that vertical plane, I will sketch something that will be padded in a few minutes. So an arc like that. And let me give this thing dimension. This is the outer radius of the bushing, so 50 millimeters, that's given to you. And then do another arc for the inner one. And this dimension is 20, uh, 9.7, sorry, 24.7, which is a little bit smaller than the radius of that shaft, 0.3 millimeter. Okay, there we are. Let's close this thing. So that's one line. Here's another line. By the way, there are many different ways of making things like that. I can draw a rectangle, could have drawn a rectangle and revolved it by 90 degrees, but I rather go this direction. So exit. Now, ordinarily, to make a solid object, what I would do is I go to part design, and part design you can make solid object. But if you're in generative shape design and I just happen to be there, there is an option for creating volumes. Okay, this is not the same as making a 3D part, but for our purpose, it doesn't matter. So volume, extrude. Notice that 10 millimeters, because we're making a symmetry consideration. So we say, okay, the only thing is that this direction of this, I want it to be flipped. So I want it to be padded to the right of that plane. Okay, why don't we apply the properties of steel on it? So let's actually go ahead and create it. I'll call it the brass analytical. No, I'll call it brass October October 25th, 2023. Okay. You say okay. Wait until it pops up in the database. It's right here, bushing October 25th, 2023. I say apply. Close that. Apply it to this piece. And let's go and input the values. There's only Young's modulus and Poisson ratio. That's all we want. I mean, obviously, problem can be done. Yeah. Okay, this is well, that's fine. So I already have something by that name. So 100,000 MPa and poisson ratio 0.34. Okay, say okay. Good. We are done here. So we're going to go all the way to the top, insert our second part, insert a new 3D part, and I'll call this thing shaft, uh, analytical. I'll call it shaft. Properties, shaft. Okay. Where's the other one? Shaft and shaft. Okay. Say okay. Let's go make it. So double click on that same vertical plane. I will sketch an arc which is radius of 50, sorry, 25 millimeter, which is a little bit point by 0.3 millimeter uh, bigger than the inside the radius of the hole here. That's why you have interference fit or shrink fit. So 25 millimeter. Okay, and if you look close enough, you see that this is by zero point 0.3 millimeters uh, inter interfered basically. Now exit, and we're going to pad. We're going to extrude that. This is surface, so extrude is if you select the surface here, surface tab. There's the extrude by 100 millimeter, except that the other direction. 100 millimeter, but it's in the other direction. Okay, good. Now, we don't have to put material on this thing because this is going to be an analytical rigid surface. It's extrusion, right? That's one of the limitations. But I do want to create a reference point. Now, the reference point, you can use these corner points, but I prefer to create a point out here so that I can easily see it. So under essential, while I'm in this part, point by coordinate minus 100 millimeter, and for y I put down 40. So there it is. This is my reference point. We go all the way to the top. We are pretty much done. We go all the way to the assembly level because I'm going to create my mesh at the assembly level. I'm not going to do it inside of the parts. Obviously, I don't have to mesh the shaft anyways, but even here, I don't want to create the mesh here and then try to use it. That's fine. I'll go all the way to the top and uh, go to the go to the structural model creation, empty FEA model. It says that there are two parts here. Which two parts do you want to, which one of the parts you want to participate? Now remember, if you cancel this thing, at some point you have to go do this thing again. So let me say both of them. And what I meant by that, if you close that box, you can actually do it from here, contributing shape, 3D shapes right there. Okay, you could have done it there, but I already did it. Okay, so we go to the mesh. I want to do a nice structured mesh here. So we go to mesh, and on the type of mesh, I will use the mesh tab. Let me, these are pinned. I don't want them to be pinned. That's why it's unpin it. Mesh. Okay, so sweep mesh. Select this. By default, it's going to select its sweeping surfaces. In other words, from from target to this other side, from this side to that side. But I don't want it to be like that. I want to do it myself. So I say manual. Let me remove these. Okay. So for the first surface, I want to use yeah. What is this thing? For the first one, I'm going to use this. For the second one, I'm going to use the one on the other side. I mean, it's just that 20 layers along the arc and thickness of, or size of 1 millimeter. This is exactly the same size mesh that I used for the tutorial one. Okay, good. That's pretty much it. Now I have to give it a solid section. So we go to properties, a solid section, select this part because it doesn't know what the material is. Now it knows. We say okay. All right. So then the analytical rigid surface. I want to show you where we are in the slides. Right there. You see this? We have to go to the abstraction tab and get the analytical rigid surface out. So here's the abstraction, and go here on the left. This was rigid body tutorial 1. That's not what I want. I want analytical rigid surface right there. You select it. And for the surface, I select this extrude. And for the point, you select that reference point that you created. Be aware of the fact that sometimes things don't work out. You may have to come back and flip this direction, but that's okay. We have no problem here. All right, so that takes care of this. We are pretty much done as far as the model and the meshing is concerned, and the fact that we declared this thing to analytical rigid surface. By the way, notice that it is defined here, analytical rigid surface. It's part of our, finite element model. Now, the next thing is you go to the scenario. So structural scenario creation. If you want to do implicit, well, if you want to do basic stuff and even implicit dynamics, all you need is to go structural scenario. Uh, Mechanical scenario is the more complicated version. There's more stuff in it we can do. But anyway, for finite element model, I want the one that you created. It's right there, 17124. This is the one that we want. All right. Now, for procedure, this says no procedure. Procedures is a static step. And remember, all I did was to change the initial time increment to 0.1. Everything else is default. These times are irrelevant. These are dummy times, really. So because it's a static problem. For boundary conditions, let's go and fix this thing from moving in all directions. So I'm going to say fix displacement. This in all directions and rotations, of course. All right. Now, these faces are symmetry planes because we took 1/8 of the model, remember? So we go here, we find the symmetry plane. And unfortunately, we have to do this in 3 times. So here is one. You have to close this, do it again. Here's the other one. Because I'm not aware of, well, I don't think you can do it multiple selection. But okay, good. Now we define the interaction. Interaction? Uh, Interaction right there. Interaction. So that's where we see this action bar. Okay, interactions. All right. We need to create first of all the coefficient of friction there. So under contact property, I'll call this thing my friction. How about give it a name that I can recognize? My friction coefficient, if you want. Then we say friction specify, and you're told that this is 0.1. Friction coefficient is 0.1. Everything else is default. Once you do the friction coefficient, then you do a surface-based contact right there. See that? Surface-based contact. Surface-based contact. Now, notice that I can go and select this, but uh, it's selected analytical rigid surface. That's good. If you select, let me cancel. Let me deselect this. One can also, for example, go and select that thing as a extrusion. You see that? It says, but it's not going to work. The moral of the story is that this must be analytical rigid surface. So cancel that. Try it again. Surface-based contact. Select this. Select this. Analytical rigid surface. Now, let me cancel that. Let me remove this. Let me select the other side of it. Let's see what it select there. Okay, that's good. But the point is that if you cannot get it from here, let me again remove it. If you can remove it, if you can get it from there, uh, uh, you can go and select it from this FEM features. You can select it from here. Either way, there are many different ways of doing it. But anyway, so that's this. Oops. Secondary surface is going to be that guy. You say, okay, don't tie them because these are contact, right? Don't do it, just contact. So a surface-based interaction has been, surface-to-surface or surface-based interaction has been created. It's right there, you can see that. Now we go and select the contact interference. You see that? There, okay? And from for surface contact, we go and select whatever was created for us here, surface-based contact, right there, the one that we just created. And then say, okay, all right. So I don't think I've forgotten anything. So let's do a quick save before we actually run it. Okay. We go to simulate. Let's do a quick model check. Make sure there's nothing obvious that's missing. No, nothing missing. Obvious. Simulation check for the same reason. Now this checking is going to start. Simulation check is going to start. And I'm pretty sure it's going to go through because I don't think I made any serious mistakes. There are some warning here. It's a good idea to look at these, but I'll keep going. Okay, this is pretty much done. The check is almost finished. Good. Says simulation checks completed. And then we're going to simulate. Simulate means run it. As soon as the dialog box opens up and you say okay, the running starts, and it's going to be very quick. Just to let you know, in tutorial 3, I'm going to be repeating the same problem except that both the shaft and the bushing are deformables. Tutorial 1, bushing was rigid body. Tutorial 2, which we are doing, is an analytical surface, rigid analytical surface. And tutorial 3 is going to be both are deformable. Okay, so I'm going to use not a solid shaft, but a hollow shaft, basically deformable. And this is now, if you click on iteration, basically you're monitoring the progress, just like you do it in Abacus. It's running now. Yep. And I want to remind you that from tutorial 1, the theoretical contact pressure came out to be roughly 600 MPa. Okay, so we're going to check that. Let me close this. So here's a situation. Uh, there we are. This is, of course, the von Mises stress. But let's look at the contact pressure. And I don't like that number. So, oh, wait a minute. Just this is very. I've done this thing before. Notice that the final answer is the very last increment. This is not the last increment. Keep going down. Keep going down. One. There we are. Roughly 600. Okay. And the contact pressure is there. Now, if you what I did first of all, let me plot something else. Let me plot the von Mises stress. Okay, good. All right, so if you want to see the whole thing, the whole shebang, without the symmetry taken into account, so you go that's what this last slide is, second last slide is. So while you're in the result, go to the display tab, results option, and do this. So what I mean by that is we are already in results, display, results option, select on that box, and then say that show me all planes of symmetry taken into account. There we are. So this is the actual geometry, okay? But we didn't model this, right? Now there's something else that I want to show you that's very useful. So let me actually uncheck this stuff. So go back here, uncheck these. Okay, fine. Now this the groups are very useful because if you look at it, say contact pressure, if you say contact pressure, for example, we can't really see it. It's there. You can see these colors, okay? So what I'm going to do, not shear, contact pressure, right there. Okay, right there. I can't see it that well. So here's what I'm going to do. I'm going to go to, I'm going to click on this, click on that, display group, add a group, create a new group. The name of it is group 2. You say okay. So if I go to a check mark, don't forget to close this thing by clicking on the check mark. Okay. If you double click on that and say, okay, don't show me, oops, don't show me the brass, for example, the brass bushing. Just don't show me the bushing. Just show me the uh, uncheck this and say replace. Now that's not very useful. Okay, let's try it again. Let's try something else. Don't show me this, replace. That's a lot better. Okay, you can see things a lot better. So the purpose of a display group is to be able to select stuff and display it based on uh, you know what you do in the group. If I go to the first one, shows me the whole thing. Second one is showing this, and you can still modify stuff. For example, let's you really have to explore this, and these are very useful. Let me do another one. So, for example, let's click on that display group, add one, display group number 3. We say okay. So let's see what we want here. Let me check mark, close it, go there. And let's say that we want, let me close this for a second. Let's plot, for example, displacement. Okay. Double click on this and say, yeah, close. So if you go to the first one, okay, you see the whole thing. There's no displacement for the shaft because it's a rigid analytical surface. The second one is going to be the this thing itself, and the third one I believe is also the same thing. Very useful. All right, so tutorial 3 is going to be repeating the same problem except that both the shaft and the bushing are deformable. Good luck.